useful later. It has a variety of applications. Students find it slightly difficult. So, but before I formally define what exactly we mean by composition of functions, let us look at one example. Here I choose three non-empty sets A, B, C. Let A denote the set of students. And B denotes set of schools, and C denotes the set of school uniform color. Okay. Now let A consist of students A, B, C, D, E, F. Set B consists of schools, say DAV school, Indian school, DPS school, Army public school, and a government school. Let's suppose these many schools are included in set B. And in set C, the uniform color are white, say grey, blue, khaki, and pink. These are the uniform colors. And now I define a function f from set A to B where fx is defined as the school. If x is the student, x belongs to set A, then fx denotes or associates the school name. For example, if A studies in DAV school, then FA is DAV. FA is DAV. And B also, let's suppose, studies in DAV school, C studies in Indian school, D studies in DPS school, and let's suppose E and F also study in DPS school. All the three D, E, F are in DPS school. And at present in our set A, none of these students go to Army public school or government schools. Okay. So do you find it is a function? Yes. To each student there is a unique school. So F is very much a function from set A to B. Though you know some schools, Army public school and government school are here where no student from this particular set is there. So that can happen. A is the domain for function F, B is the codomain, and the range is a subset. So are that condition satisfied? Now I define another function G, from G is defined from set B to C. And what does B do? That B, say if I denote the element of B by Y, then it associates to each element Y, each school Y, the color of the uniform, an element of set C. For example, the DAV school uniform is of white color. Indian school students are wearing grey color. DPS students have blue color uniform. Army public school also have blue color uniform. Government schools have khaki school uniform. And this pink color, whatever schools are under our consideration in set B, none of them have a pink color uniform. So it may happen. So you may again verify that G is a function from set B to C because each school of set B has been assigned some particular color of uniform. Okay, though in set C some color like pink color may not be assigned to any particular school. That may happen. So it is very much a function from set B to set C. So I have set this situation that there are, I repeat as now, that there are three sets A, B, C. A is set of students, B is set of schools, C is the set of uniform color. Each student is assigned a particular school and each school has set its uniform for a particular color. Now what is my question? My question is that directly if I ask you that is an element A of set A, that is student A, I am asking you directly, student A, take small a, student A is wearing which color uniform? If I just, ask somebody, by your child, what is the color of your child's uniform? Or ask to a third party, what do you think that what should be the color for? He may ask if he has some knowledge of the color of the uniform of different schools, where you are studying in which school. So first of all, you need to know in which school he is studying. That is, you need to know FA. What is FA? FA assigns the school. And once you know the name of the school, then only you can find out the color. And which functions assign the color? The function G assigns the color. G assigns the color to each school uniform. Do you find? Now let us work out G of FA. Now what is FA? The student A studies in which school? DAV school. And what is the uniform color of DAV school? It is white. So what do you find? That here directly an element A, small a belonging to set A, is associated to the white color which belong to which set? C. By virtue of two different functions G and F taken like this, GOF. So now I can say GOF of A is white. So when we have two functions working one after the other, then to this situation we say that we are making use of composite functions. Now let me formally define what exactly we mean by composition of functions. Please note down, let A, B and C be three non-empty sets, and let F is a function from set A to B and G is such that B to C. Then the composition of function F and G is denoted by GOF and is defined as GOF such that A to C, and given by GOF of X equal to G of Fx, where of course X is any element of set A. So this is the definition of composition of functions, and I have already discussed with you one example pertaining to the case I have discussed. I repeat formally now, what do you mean by GOF of A? Where A is a student in set A. So it means G of FA. Now what is FA? FA means student A studying in which school. So it is G of A studying in which school? DAV. And now what is the job of G? The function G assigns you the color of uniform. So what is the color of DAV school? That is white. So directly an element small a of set A gives you an element C of color, that is white. So that's how, that is the simplest kind of example of composition of functions. Now after defining composition of functions, please note here, what is the domain of a domain? What is the domain of function f? Domain of function f is set A. And what is the range of function f? Range of function f has to be, please note, the range of function f has to be a subset of domain of function g. Then only GOF may be defined. So what have you noted? that GOF is defined, then range of F has to be a subset of domain of G. Now let us take one more example which is more mathematical to express you, to clarify you the idea of composite functions. Take an example. Here is given is a set A, a set of real number except a number 3 by 5, and a set B, again set of real numbers except 7 by 5, and a function f is defined from set B to A such that fx equal to 3x plus 4 divided by 5x minus 7, and a function g is defined from set A to B such that gx equal to 7x plus 4 over 5x minus 3. And here the symbol IAX, the identity element on set A, x is x. Identity element means that any element of set A associates to itself. And what do you mean by IB of x equal to x? That every element of set B is associated to itself under IB. Then IA is the identity function on set A and IB is the identity function on set B. So under all this given, we have to prove, number one, that FOG is IA and GOF is IB. That's what we have to do. Now before I proceed further, let me tell you that when he says given is a set A equal to R set of real number except 3 by 5, what does it mean? See here, Gx is defined from set A to B. So and in set A, you know, in Gx, what is the denominator? 5x minus 3. 5x minus 3 should not be equal to, denominator should not be equal to 0. So if 5x minus 3 equal to 0, for which value of x? For x is equal to 3 by 5. So for Gx to be defined from A to B, here x may be replaced by any real number here, but so that denominator should not be 0. That means x should not be equal to 3 by 5. That's what he means here. Similarly, f is defined from B to A. So here the denominator 5x minus 7 should not be equal to 0. That is, x should not be equal to 5 by 7 by 5. That's what conditions he is giving you. So there is nothing to get worried about it. Automatically it will get adjusted, but you should know why he is defining the domain of f and g like this. And now let us see. We have to prove FOG is the identity element IA and GOF is IB. So I start with GOF. Let us work out GOF. GOF of x. Now GOF of x, what do you mean by GOF of x? As I have just defined, it means G of fx. You simply to apply the definition. What is the definition of function fx? Fx is defined as 3x plus 4 over 5x minus 7. This is fx. And now we have to find the G image of this. Now what is the definition of Gx? What is the definition of Gx? The definition of Gx is 7x plus 4 divided by 5x minus 3. And when we are finding GOF of x, we have already applied f, so we are at this step. G of 3x plus 4 over 5x minus 7. And now to apply G image of this, here you replace x by 3x plus 4 divided by 5x minus 7 in the definition of gx to get 7 times 3x plus 4 divided by 5x minus 7 plus 4 the whole divided by 5 times again the same 3x plus 4 divided by 5x minus 7 minus 3 and you take LCM in numerator and denominator and cancel and work out. You know all this you work out. Take one or two more steps. I'm sure you can do it and you will get 41x by 41. 41 and 41 cancels. You get x. So what do we get? That GOF of x is x. And we applied GOF on what? B to A. First we applied on B. So if every element x is associated to itself, we can say that it is IB. So we can conclude that the composite function GOF is IB, the identity function on set B. And similarly, now let us find out FOG. Now work out FOG of x. Of course on A. So now what is the definition of Gx? It means f of Gx. So first we apply the definition of Gx. What is the definition of Gx? It is 7x plus 4 divided by 5x minus 3. And now to find out the f image of this, you replace x by 7x plus 4 divided by 5x minus 3 in what? In the definition of fx. What is the definition of fx? Definition of fx is 3x plus 4 divided by 5x minus 7. So you replace this value of x over here. So you will get 3 times 7x plus 4 divided by 5x minus 3 plus 4 divided by 5 times, you replace the same value of x here, minus 7. Take LCM in numerator and denominator and cancel and work out. And again you will get 41x. You just take one or two more steps. 41x by 41. 41 cancels x. So what do you find? That FOG of x and being applied on A gives you x. So FOG is nothing but the identity function of set A. So we have proved that GOF is IB and FOG is IA, and that's what is required to be proved. Now before I shift from the definition of composite function and introductory examples, please note few points. Number one, if f is a function such that A to B and G is a function from set B to C are both 1, 1, then GOF from A to C, the composite function GOF from A to C is also 1, 1. I repeat that if we have two 1, 1 functions, f from A to B and G from B to C, then the composite function GOF from A to C will also be 1, 1. And similarly for 1, 2. And similarly the second point, that if f and G are both on 2, then GOF will also be on 2. Of course, f is from A to B and G from B to C are on 2, then GOF from A to C will also be on 2. Now third point, if f and G are functions such that GOF is defined and 1, 1. Now remember, here he is not talking in advance anything about f and G separately, that whether they are 1, 1 or on 2 or what. He is saying that if GOF first of all is defined and is 1, 1, is defined and 1, 1, then f is 1, 1. And we are not saying anything about G. Nothing about G. It may or may not be 1, 1. And likewise the fourth point, that if GOF is defined and on 2, then G is on 2. And we are not having any comments about F. I repeat, that if GOF is defined and onto, then G is onto. So please make a note of these 4 points.